Well, I want to welcome you to the globalFACT Forum Live Symposium here at the 25th IIR International Conference of Refrigeration. My name is Jordan Smith, and I serve as Executive Director of the Global Forum for Advanced Climate Technologies, known as globalFACT. Our organization promotes education, awareness, and policies that support the important role of new generation, low, and reduced global warming potential advanced climate technologies in protecting the environment while meeting the rapidly increasing demand for safe alternatives. We are pleased to be here today to provide information and engage in a dialogue about our panel topic, Understanding Refrigerant Policy Drivers and Practical Implications. Today's symposium is an important addition to the information and programming that globalFACT has been providing to users, policymakers, and the public since our launch last year. We invite you to visit our website at globalFACT.org to learn more about our organization's recent activities. I'm happy to be joined today by our keynote presenter, Jim Wolfe. Jim has 50 years of experience in building technology, refrigerants, and energy efficiency compliance. He has been engaged in critical climate change policy matters throughout the globe, including the Montreal Protocol and Kyoto Protocol. Jim has served as the chairman of the International Policy Committee of the Business Council for Sustainable Energy, is former president of the American Society for Heating, Refrigerating, and Air Conditioning Engineers, known as ASHRAE, is former chairman of the Alliance for Responsible Atmospheric Policy, and is a recent recipient of the U.S. Environmental Protection Agency's Award for Leadership in Ozone Protection. Jim has a Bachelor of Science in Electrical Engineering from the University of Arizona and an MBA from American University in Washington, D.C. If you have questions for Jim, you can share them by emailing them to questions@globalfact.org. We'll have a Q&A period following the presentation. And with that, I want to thank everyone for joining, and I will turn it over to Jim.
Let's start with a little discussion on global policy. In fact, what got us into this mode of operation of changing from one refrigerant to another, one technology to another, was the fact that we had to start addressing additional issues related to selection of our refrigerants and our technology. Those were environmental issues. For example, the Montreal Protocol, which was passed in 1987, the purpose was to reduce the problem we had with ozone depletion. And it just so happened that the CFCs and HCFCs we were using in our technology in refrigeration and air conditioning, automobile air conditioning, home air conditioning, so forth, have fairly high ozone depleting factors. And so those needed to be phased out to address that problem. And so we've been going through that process of phasing those out. Now, when we did that phase out, we didn't really take into account the fact that they had global warming potential. So we moved from CFCs and HCFCs to HFCs, which had global warming potential equal to not the CFCs, but the HCFCs. And now, because of new environmental challenges and new environmental policy related to global warming, we're moving from those HFCs to HFOs and to natural refrigerants and other things. So we'll be discussing that. So from a domestic standpoint, after there was a recognition that we needed to address the global warming potential of these refrigerants, the EU moved first, really. They moved in automobiles first, and then in 2006 they had an F-gas regulation. And the purpose of the F-gas regulation was to start the phase out of the HFCs in industry. And they started out with auto air conditioners and with aerosols and so forth. And you'll see that below that they did a part 2 to that gas. Australia put a tax on HFCs, and it lasted for 2 years, became a political problem. They took it off. But it created a recognition that they needed to address the HFCs. So they've been moving quite rapidly to get out of the HFCs. California has passed a law that said they'll have a 40% reduction. They also have some proposed regulations on specific timing of when you have to stop using HFCs and certain technologies. And we can talk about that later. And then we had a second F-gas regulation with a 79% reduction. And then Japan has a top runner program. And then even in the USA, we had regulations by EPA, which were SNAP rules 21 and 20, that were going to phase out in some of the home appliances and in chillers, the use of HFCs. Subsequently, that was thrown out by the court. But as a result of that activity, California has been moving forward, and some of the what we call climate alliance states are beginning to implement 20 and 21. So we have this, and Canada just issued a proposed rule on HFC and refrigerant management. And we could talk specifically about that. So the framework here is policy evolving globally, policy evolving domestically, and in the United States, in one particular state, which is very significant. And so it's a recognition by the equipment suppliers and refrigerant manufacturers that we need to change our technology to address the global warming problem with the chemicals. Now this is not a new process that we've been following through. Initially, when we were searching for ways to do air conditioning and refrigeration, as back in the 1800s, they had a number of natural refrigerants. That's before the fluorocarbons came into being. Some of those were difficult to use, some were a little bit dangerous, and some didn't provide the performance that we'd like to have. Some are still being used today. In the 1930s, we got CFCs. Then we evolved into HCFCs, needing a different refrigerant for different applications. You see, there's no one refrigerant that can do everything for us in all of the applications. And then we moved into HCFCs because of the Montreal Protocol. And now because of the Kyoto Protocol and these additional policy things, we're moving into the HFO, addressing that we want low GWP solutions for our technology. And it's creating some problems for us, some challenge for us, and we'll talk about that. We have a business challenge. The business challenge is that there's uncertainty. All of this regulation is not firm yet. We don't know what countries are going to do to get out of the HFCs as a result of the Kigali Amendment. We don't know exactly what California is going to do. We don't know what other states do. We know a transition is happening. We have uncertainty. We need to get the technology in place. And now we need to have a technology that is not only sustainable for consumers and business, but sustainable for the environment. So we have to weigh many factors. We have to look at the current and anticipated regulatory requirements. And by the way, industry is ahead of the policy in developing alternatives. And you'll see that as we talk further. We need products that are effective and cost effective. And they have to be safe. And we have some new challenges that we didn't have before we had to worry about global warming. And we need to have the resources and the time to do that. So what would be the trade-offs? What's an ideal refrigerant going to look like today in terms of satisfying these needs? We've always had a concern of cost. We want to provide the function at the lowest cost possible. We want it to be non-toxic, so it's safe. We want it to be non-reactive, so that it doesn't damage the equipment. It needs to be thermodynamically efficient, so we have a cost-effective, efficient product that doesn't contribute to global warming from that standpoint. It needs to be chemically stable. It needs to be compatible with the various materials that we're using in our technology. It needs to be safe for the users. Now, in the past, we didn't worry a lot about that because we had alternatives that were very safe in all respects. And now we have some minor challenges, and we need to have it environmentally safe. The considerations for the fluid selection gets complex. We have the performance requirements we've had in the past. We want durability. We want the availability of the technologies. We have all these factors that we've needed to address in the past to select our fluid. A lot of things we need to consider. Now the environmental policy has imposed some additional requirements, and that is affecting the safety of what we do. So what we have is a very simple situation. For most applications in refrigeration and air conditioning, we could use what we called an A1 refrigerant. This is the classification from Standard 34 from ASHRAE. So we had all these refrigerants that were very low toxicity, practically, for all purposes, non-flammable. They will burn under some conditions. All refrigerants will burn under some conditions, but not create any kind of a dangerous situation. And then we had A2 that were flammable, that in the past we didn't want to use because it was going to be more costly, and we had concerns with the flammability. And then we have A3, which are the hydrocarbons that can be used in some limited applications based on the charge and the safety considerations. And so we wanted to come up with a solution rather than using flammable if we could, and so ASHRAE 34 came up with a new classification, a subclassification A2L, mildly flammable. I call it slightly flammable because it doesn't create a real risk, but we're considering it in worst case and being very conservative. Now, an A2L is a refrigerant that has a burning velocity of less than 10 centimeters per second. And in fact, it burns very slowly. And if you put a match to it and get it burning and take the match away, it goes out. It's not something that is going to cause a serious fire situation. And we have some candidates for it, and we'll talk about that. So our challenge is take this new category of refrigerant and come up with solutions to replace all those A1s that we used in the past that had relatively high global warming. So we have this right balance. This is some of what you saw on the other slide, but I want to emphasize the fact that we still want the zero ODP, we want the GWP as low as possible. Now, some of the things we're going to start using in the future are still going to have a fairly significant GWP until we can find solutions to go low. We may be in a 750 GWP versus an 1800 or 2000 that we're using now, and we might want to in the future hope that we can get down to 5 or 10 or less, and in some categories we can, depends on the technology. So what refrigerants are desirable? Based on the policy, forcing us out of those that were highly desirable and we thought ideal in the past. Well, in the past, fluorocarbons could satisfy all of our needs. And of course, we used other refrigerants too. In the future, we're going to be using a variety of refrigerants, fluorocarbons and other refrigerants. There'll be trade-offs required. So it's really going to be a cost, efficiency, safety situation. And there's various options. We have the fluorinated hydroolefins, fluoroolefins, like 1233ZD and ZE for chillers. And then we have blends that we can use. So we need a solution for 410A for the unitary equipment, and that's the challenge where we're going to need to use the A2L refrigerants. We have hydrocarbons, propane, so forth, ammonia, CO2, and they have applications, and we'll probably expand their use as long as we can keep everyone as safe as we have in the past. What's the industry doing about this? We've got this challenge. Well, first of all, we're developing the new HFO refrigerants. Looked at hundreds of candidates worldwide, zeroing in on which one is best for which technology. Refrigerator, home air conditioner, chiller, residential air conditioner, so on and so forth, and refrigeration. And there's going to be a variety. We're going to be using more refrigerants we did in the past. And then we're conducting research because we need to know what's different about these refrigerants. How can we use them as safely as we've used the ones in the past? So we're developing data by doing research on what kind of charge levels, will they ignite, how severe is the ignition, if it hits a hot surface, can you sense it? All of the things you need to know to change the standards like ASHRAE 15 or the ISO standards so that we can use them as safely as we've used others in the past. And after we get all those standards developed, we need to change the codes. Now in the United States, that's a lengthy process. And so it's going to take time to do that, to get the research done, standards changed, and the codes changed. Well, in addition to that, we need to train people. Will there be different things they need to do with these refrigerants in the past? We have to change the equipment a little bit for sensors, with ventilation, so on and so forth. So the industry recently developed through AHRI, the Trade Association for Manufacturers in the US, a program which is called Safe Transition. And it's being developed to assist the safe transition to these mildly flammable refrigerants. And they're looking at everything you can imagine. They have a major task force, and then they have 7 subcommittees. And if you're interested in being involved in these, you can contact AHRI. So we'll get people trained, we'll get the information out there, we get the codes, we get the standards, and we'll get these new refrigerants in the marketplace.
If you do have questions, please send them directly to questions@globalFACT.org. Jim, I'm going to start, actually, if I can. Clearly, as you talk through the challenges in transition, and as folks look to the ultimate goal of lowering GWP, there's a balance. It's looking for a balance of ensuring safety, ensuring, and looking at cost considerations, looking at energy efficiency. I want to start a little bit with safety, and I think you started to touch on it with AHRI's initiative, but the question really is, what is industry doing to make sure that the products that they're producing now, as they make this transition, are in fact safe?
Okay, the first effort that was done by AHRI was to come up with information on, and a survey globally. What do we need to know about these new A2L refrigerants to use them safely in applications? And as a result of that survey, they got 20-some different recommendations for areas that need to be investigated and set a priority, and 10 of those are being addressed today. They're being addressed in the US, and there's research happening in other parts of the world. DOE is doing some research, AHRI is doing some research, and ASHRAE is doing research, about $6 million of research. And I just want to refer to a sheet here that I have that will help me be a little clearer on what that research is, so that, okay, just to give you an example. One research is, under what conditions will an A2L ignite? So that's going to help you know where you can apply it in the equipment. What happens if an A2L hits a hot surface? Will there be any conditions where we need to design the equipment to protect so that if there's a refrigerant leak, it doesn't hit a hot surface? What about leak detection? What kind of leak detection or sensing is necessary in an equipment room, in a piece of equipment, in an occupied space? And is that equipment available today to do an adequate job? And so they did investigate, and there's a continuing project on that. So that was the AHRI, and ASHRAE did research on, okay, if we have an ignition, how severe is it going to be? Based on the type of technology, based on the refrigerant charge, so on and so forth. How do you service this equipment? What do we know about what was done on the A3, the hydrocarbons? So do we have to service this equipment like that? What do we have to do there? How do you install it? Do you use different kind of fittings, like flare fittings, compression fittings, press fittings, braze fittings? Which one's the best to use for these type of refrigerants? And then also, if you have a fire and this equipment catches on fire and the refrigerant burns, is that a risk? And then DOE, what's a charge level we could allow? So all of this information is being developed. The standards being written, ASHRAE 15 and now a 15.2 for residential. And as a result of that research, and there's already been some changes, some addendums, there will be addendums to the standard that will help the building code people put in place the requirements that are necessary to make sure that we're all safe. And then, of course, the manufacturers are already designing this equipment, testing this equipment. And then there's going to be training through the AHRI. There's going to be educational work that's going to be done. There are going to be seminars, educational programs, much like globalFACT will do on your general areas. So that's basically everything they can imagine. It's a very extensive program that AHRI is doing. There's something like, they have, just for your general information, they have a Safe Transition Task Force they formed. It has an Installation Operation Maintenance Working Group, Codes and Standards Working Group, Bulk Storage Manufacturing Storage Group, DOE Shipping Package Handling Group, Recovery Reclaimed Destruction Group, and a Safety Training Group. So you can see this is quite extensive. Long answer to your short question.
No, but a good one. Thank you. And I'm just going to lob out another. So again, as we think about some of the challenges to transition, one of the areas that people are looking at is energy efficiency. Can you talk a little bit about how some of the new products that are coming to market compare from an energy efficiency perspective?
Sure. In some, it's kind of interesting, because if you go all the way back to the CFCs and HCFCs, we had never optimized them on energy efficiency. So if you had actually optimized those, the ones we're using today that have been mainly optimized, like 410A in your residential, 134A in chillers, they wouldn't be as efficient as the CFCs and HCFCs, but they actually are today. They're very energy efficient, and the substitutes we're looking for, and as I said, we look for hundreds of blends to come up with energy efficiency. with changing technology, improvement in the technology, you're going to see the same energy efficiency or better that you saw in the past. Now, will we be able to get as good as we could have gotten by optimizing some of the older refrigerants? No. But we're going to be better than we were in the past. So energy efficiency looks good. It's a very strong consideration. And a lot of the options that didn't provide the energy efficiency were just discarded because we realized we had a standard we need to meet, and they need to be cost effective when they're energy efficient. The energy efficiency isn't the only factor. You can get energy efficiency at a very high cost, or you can get it at a comparable cost.
Sure. And actually, that's a good segue, because there are concerns that some of the newer products will be more expensive. And so wondering what your thoughts are on that.
It's an interesting thing with products. As you start mass producing products, the prices seem to come down. I was at a store the other day looking at TVs, and I could buy a 50-inch TV for $350. And think of what that was when it came out originally. And that's what's going to happen to our technology. What happens is it's going to be cost effective. Because we're going to optimize the refrigerants to the application. And as I say, we're going to improve the technology, heat transfer, gas flow technology, all of that will be improved and redesigned. What we learned when we went from CFCs to the HFCs, that we had technology and techniques that we hadn't used in the past, and that we could build a lot better technology. And so we came, and with the new electronic controls, we came out with a lot better technology, and that continues to happen. So I think from a cost standpoint, there may be some short-term additional cost to handle safety, but in the balance, I think we'll get to about the same cost.
Okay, thanks. We have a question from the audience. This is on the topic of flammability. The question is that A1 fluids are called non-flammable, but they can combust too, correct?
Well, I don't like the term combust. I would say they can burn too. When you get a high enough temperature, you can burn almost anything. So what we've learned in some of the preliminary research looking at A1 versus A2L in a burning situation, we believe that the actual effect of the burning of those two will be the same, but we have to burn the A1s at a much higher temperature. It has to be a higher temperature. But if you have a big fire, it's going to burn.
Sure.
But with the A1, what happened, I like to explain it this way, and this may not be 100% accurate, but I think this sort of illustrates it. If you're aerosoling an A1 refrigerant and you put a match to it, the match goes out, right? It's not a high enough temperature to keep it burning. You put it to an A2L under the right conditions, the refrigerant will burn. Take the match away, it exhausts. You put it with some of these other refrigerants, like an A3, you get a lot of burning. So anything will burn at a high enough temperature. But it's such a low risk that the research is showing us that it's not going to be a problem.
Thank you.
The theme of balance and optimizing came through in a lot of your charts and the information. I want to go back to cost for a minute, and given that long-term prices will come down, things will get affordable, is there anything that can happen in the short term, next couple of years, 5 years, to help us get over this transition? I'd point out California put in some pretty aggressive proposals, and then they came up with incentive money, but it was like $1 million, which is a drop in the bucket. You can maybe convert one supermarket from a 404R22 to a lower GWP technology with that. So given all this balance, who's going to end up paying for the short term? Do you think, is there anything other than, I know there's some utility incentives going on, how are we going to get through the short term cost?
That's a very challenging question, and you likely have as good an answer as I have. I would hope that there could be more incentives. The problem in the U.S. is that we don't have a uniform requirement. So if we as manufacturers are going to supply equipment to California early, it's going to be more costly. I don't know how you can overcome that. The way you get costs down is get the volume up, as you know. I mean, that happens with the competition in your industry. It happened with 134A. It's going to happen with the other refrigerants. And as we go globally, everybody building these products, then the cost will come down. But in the short term, in the U.S., I think I agree with what you alluded to, that it's going to be a concern to address that, and the cost will be more expensive for that equipment initially. I don't know if you know what the requirements in California are proposed, but I just want to address that because I'll show you the challenge is right, and these are changing all the time. So I have that disclaimer, but as I understand right now, is there's a possibility for air conditioning systems, like for your home air conditioner, they may have a requirement in place that you can't use a 410A in 2023. That's not going to happen in the rest of the U.S. In fact, it's going to be difficult to have building codes that will, allow that use. And for chillers, it would be beginning 2024. And it's not a problem for chillers. It's kind of interesting. For chillers, we have some non-A2L solutions. And in some cases, in one case, in a chiller category, the chiller actually doesn't need to cost more than they did in the past because the capacity was increased 30% by the new refrigerant. So you take a 30% increased capacity, that can bring your price down. And then for refrigeration, they have 2022. So those are challenging dates that need to be addressed.
You mentioned about energy efficiency, and I guess looking at what has motivated move to GWP is about reducing greenhouse gases, and if your energy being produced is from a coal-fired power plant, is there a terminology that is used with refrigerants or refrigeration system that captures the overall greenhouse effect of that refrigerant, which includes the refrigerant characteristic in terms of it escapes to the atmosphere, but also the energy use in operating with that refrigerant? Is there an overall term that the industry is developing for that?
Well, there's been an evolution of terms, and it's not only the equipment. You could talk about a building, also in the same context. We started out with a term that was called TWE, and then we went to life cycle cost analysis, and now there's a term. What is the term? Somebody remember that? It's the one with global warming in it that TEEP has been talking about in the Montreal Protocol. Anyway, what it does, yes, what is the term?
One that I'm hearing about now is LCA, or life cycle assessment.
Yeah.
And they're looking beyond just the CO2
life cycle
impact.
climate
They're
performance.
looking at water, air, ground,
Right,
everything.
right. So it's life cycle. So basically, you go cradle to grave, or you could say, cradle to grave, where you're taking the manufacturing cost, what it takes to get the material out of the ground. And as you alluded to, the fossil fuel situation, which is changing from time, and you really have to look at every utility, what the composition is. So that's a term, but it's frustrating to me because it's never really caught on. It doesn't, when we go to the Montreal Protocol meeting and talk about energy efficiency and try to talk in that terms, it doesn't seem to get integrated into the policy. We all understand that the refrigerant, if it's released to the atmosphere, has a global warming potential. We all understand that the technology consuming electricity, if it's from the burning of fossil fuel, contributes to the global warming, but we haven't really gotten the policy to bring that into place.
Hey Jim, you've been around a long time, I see, 50 years. One of the reasons we got into this situation with CFCs and HCFCs, et cetera, was because the systems were fairly leaky, and we didn't worry too much about refrigerant emissions because the refrigerants were safe and they were inexpensive, and then the ozone depletion issue came along. And I wonder, in your experience, have you seen a pretty significant improvement in just the amount of leakage out of systems that, it's been improving over the last few decades? And so that also helps with this transition because it's easier to use these lower GWP refrigerants safely because the systems just aren't leaking as much as they used to 30 years ago?
That's a very good question, and it's kind of an interesting question because there are two parts to that. The first part is, does the equipment leak as much as it used to? No, I mean, it's tight. Every manufacturer, you think of a refrigerator, you put a refrigerator in your home, you don't expect a refrigerator to leak, right? You do expect, in the past, didn't you expect your auto air conditioner to leak? It doesn't leak as much now. And the air conditionings in your home don't leak. If you buy a packaged air conditioning unit, it likely will not leak. If you buy a split system, if it was installed in right the first time, it either leaks or it doesn't leak. Often you have a problem from the installation. So the second part is the installation and taking equipment out of service or servicing it. The problem we have, even in the United States, where there are strict requirements that you have to recover and recycle, and if you have a leak, you have to repair it or replace it. It's all in the EPA rules, and that's encouraged people to improve it, and they have improved it. We still have situations where people blow the system charge when they service. So a lot is going to be done with these new refrigerants to emphasize the point that you must control that refrigerant. And now, because it's mildly flammable, maybe we can get their attention of the service people. And that will improve it. The equipment is built well. I don't know how we can improve that over what we're doing today, but we can do a lot on the servicing side, and we'll be doing a lot of education on that.
You just said that you think, or you say that the equipment is tight, you don't have any leaks during the operation, then you could use ammonia or hydrocarbons safely, and the efficiency would be better than for HFO. So, I mean, you call it globalFACT, but you go to Europe and you see a lot of supermarkets running on CO2. You see chillers running on ammonia, chillers running on hydrocarbons. And
I agree with you that if they're tight and they don't leak, then you use safety. Another component that needs to be considered, and we've had a lot of discussion with the fire marshals. They're very concerned what's in the building. If there's a fire, what happens? So conditions would be different if you had a hydrocarbon piece of equipment in your building and there was a fire than you would with one that had less flammability. So there's that aspect. I will remind you of what happened in Europe, and I'm sure you're well aware of this. When they came out with the first regulation on HFCs, it was a two-part regulation. The first part said, okay, for auto air conditioners, right, Barbara, we're going to phase out HFCs. But for the rest of the industry, the stationary air conditioning, we're going to allow you for several years to tighten your equipment because there were massive leaks. With that sort of unstated promise that if you can demonstrate that you can operate that equipment and not lose the charge, perhaps we won't regulate you. Supermarkets were the major concern. You know how supermarkets are. It used to be that they just had a tank of refrigerant feeding the system because it's a distributed system with miles of connections. Apparently in Europe, you weren't able to accomplish that because now they're regulating you out of the other systems, the transport systems and the HFCs out of that. So we haven't, as an industry, been able to convince the policymakers that we can keep this stuff tight and service it and not lose it. So that's where the problem comes. I agree with you. If it's tight and doesn't leak and you handle it properly, what's the problem? But the problem is it isn't being done. And think about other countries. Think about going to some of the developing countries. What do you think happens there with the servicing of the equipment and the management of the equipment? It just isn't done. So this is regulated from a global worst case. You know, we're going to have people installing, and people have been putting hydrocarbons in 22 air conditioners and blowing them up. So, you know, we have to handle the worst case, and we haven't been able to build the credibility.
You also know that they investigated the split air conditioners in China, for example, and India, and you nowadays have manufacturers, 2 manufacturers in China, 2 manufacturers in India, manufacturing split air conditioners using propane.
Yes.
And they with the investigation they did at the Fire Research Institute of China, they concluded that it's 10 times more safe to use propane in a split air conditioning system than using isobutane in domestic refrigerator.
Yeah, I don't.
And there are 1 billion domestic refrigerators worldwide running on isobutane.
Yeah, I understand that, and we're building more information. I don't have all the knowledge that you have on that. I think that's a continuing learning process. We're very conservative in the U.S. Canada is very conservative also, and the building codes are very conservative. So it's a difficult process. But I agree with you. It's something that needs to be considered, and there are applications for everything. And I think it's a matter of comfort, cost, efficiency, safety. Yep. Okay. Thank you for the question.
Other questions from the audience? I'm going to ask one for you, Jim. So as new refrigerants are developed, there's this term that some use, future-proof. Do you believe that any refrigerants are actually future-proof?
Well, maybe in my lifetime, but maybe not in yours. So what happened is, we thought we had the perfect refrigerants. We thought 22 was an absolute wonderful refrigerant, wasn't it? That was perfect, wasn't it? Until we had the environmental concerns. So what will they come up with next? I don't know. You can't have certainty. So the answer is, we don't know what's going to happen.
Well, Jim, I want to thank you very much for your time and expertise today. I want to thank everyone for joining. Again, feel free to visit our website, globalFACT.org, for additional information about our organization, our efforts, and our programming. And that concludes today's presentation.